Okay. So this is the outline of my talk. I want to give you like a brief introduction into universality in general terms, and then universality as I will use it throughout this talk with reference to threshold bound states and Efimov physics. And then I want to apply these ideas to the Hypertriton. First, looking at the structure of the Hypertriton, and from this analysis, we will learn that there is an additional approximation that can be made in order to study the lifetime puzzle and do that in a somewhat simpler theory. And then I'll end with a summary and an outlook. This work is in collaboration with Fabian Hildenbrand, who got his PhD just last year at TU Darmstadt. He's currently a postdoc there. And there are some references on this work on hypernuclei, and also the first one is a general reference on universality if you're interested. So let me first remind you of the principle of universality in physics. And you all learned this in statistical mechanics. Physical systems with a very different short distance behavior can exhibit identical behavior at large distances. Usually this is taught in the context of critical phenomena and critical exponents, but the concept of universality, of course, has wider applications in physics. And one flavor of universality that is closer to what I want to talk about is what is used in the field of ultra-cold atoms. As you know, at low energy, the interactions are at low enough energy determined only by the scattering length. And for example, if you look at the properties of a dilute homogeneous Bose-Einstein condensate, so here is a picture of the velocity distribution from the first experiment that was done at Gila. Then you can describe the properties in an expansion in rho a cubed, where rho is the density and a is the scattering length of the atoms. And for the energy per particle, you have a universal result that only depends on the density and the scattering length, apart from the mass of the particle and h bar, of course. And there are universal corrections that are corrections proportional to rho a cubed, which is a small parameter for a dilute gas. But of course, there are also non-universal corrections. This would be corrections that are determined by other interaction parameters, such as the effective range. And for the condensate fraction, you can get similar expansions. So this is kind of the type of universality I want to talk about. If you think of that in terms of wave functions, it means that we're looking at physics that is controlled by the tail of the wave function. So in a sense, this is where the tail wags the dog, because the tail of the wave function is all that matters for the observables we're going to look at. Now, in particular, I will be considering the unitary limit. So let me first define what the unitary limit is. Consider a system with short-range resonant S-wave interactions. Then the unitary limit is a hypothetical limit where you take the scattering length to infinity. So you make the interaction as strong as you can. And at the same time, take the range of the interaction to 0. So the range of the interaction here is displayed by this variable L, and all the other effective range parameters then also would go to 0. So you just want the scattering length to be large. Of course, this is not a physical limit. There is no physical system that is in this limit, but it is a useful limit to expand around. If you want to reach that limit theoretically, One way of doing that, you think of a potential, let's say some squirrel potential with a finite range here and some bound state at a finite energy. If you take the range of this potential to 0 and make it deeper and deeper such that this bound state ends up directly at threshold, then you would be in the unitary limit. Now, there are some special features of this limit. So if you look at the scattering amplitude, which of course for short range interactions can be described by the effective range expansion, you see that all these terms here that make up k cotangent delta go to 0, and only this unitarity contribution remains. So there is no dimensionful quantity in the scattering amplitude apart from the momentum itself, which means it's scale invariant. And it also saturates the unitarity bound. So this is the maximum scattering that is allowed by unitarity. This is where this limit comes from. And what I want to do is to use this limit as a starting point for description of few-body systems. So let's take the scattering length finite, but large and much larger than the range of the interaction. And as you know, there are quite a number of systems in nuclear physics that are also at least reasonably close to this limit. Then you get a natural expansion parameter, namely you can expand in this ratio L over A, which characterizes the unitary limit. And also, of course, you will have other expansion parameters. If you go to finite momenta, you will have additional contributions in terms of k times L and so on. If A is positive, you know there is a universal dimer with an energy that scales like 1 over A squared. The tail of this bound state wave function of this universal dimer has this form, e to the minus r over A divided by r. And this is the tail of the wave function that will determine all bound state physics. Now, of course, that's not the whole story. And there are corrections to this from finite range interactions and any other physics that might be important. These will be able to include in higher orders. There is one additional complication that comes into the game in some systems. And the simplest system where that happens is if you have 3 bosons. And this was first realized by Efimov in 1970. And the easiest way to see this is if you go to hyperspherical coordinates. So this is just an analog of going to regular spherical coordinates, where let's say you have a 3-particle system, take out the center of mass, then you have 2 Jacobi momenta, which are 6-dimensionful coordinates. And instead of the 6-dimensionful coordinates, you take this hyperradius, which is the sum of the squares of the 3 interparticle distances and 5 angles, which are called hyperangles. And these coordinates are useful to analyze that problem because if you look at distances in the hyperradius that are large compared to the range of the interaction, but small compared to the scattering length, the corresponding Schrödinger equation only depends on the hyperradius. So these hyperangles drop out of the problem. You get a one-dimensional Schrödinger equation with a 1 over r squared potential. Now, you might know that this 1 over r squared potential, if it's attractive enough, is a singular potential, which has problems with uniqueness of the solution. So you need to renormalize this problem, very similar to what you have to do in many quantum field theories. And this means that you have to take an additional input to fix the ratio of these 2 solutions that you get here. And the way that Efimov did this is by requiring a boundary condition here at short distances on this wave function. But this boundary condition of course, breaks the scale invariance that we have in the unitary limit, because now we have this, let's say, the logarithmic derivative of the wave function fixed to a certain value at this radius r, and this is a dimension-full parameter that we introduce in the problem. So the scale invariance is gone. If you want to interpret this physically, of course, a boundary condition on the wave function dependence on the hyperradius is nothing but a short-range three-body force, because you can only reach a small hyperradius if all three of these interparticle distances are small. If one of them is large, you still won't have a small hyperradius. So this really is nothing but a contact three-body force, since it modifies the interactions of the particles at short distances. But what you find is that this scale invariance is not fully broken. There is some remainder of the scale invariance that remains, and we'll see that on the next transparency. Clearly, for such system, the universality concept must be extended. Physics is not only determined by the scattering length anymore, but you also have to include whatever piece of information you use to fix this boundary condition. So a different way of looking at this is if you go to momentum space and think of this boundary condition as a three-body force, which I just motivated, with a coupling constant h of lambda, and of course this coupling constant will be a running coupling constant. And now I switch from this position space cutoff r to a momentum space cutoff lambda, which is proportional to 1 over r. And then if you look at the behavior of this coupling constant, you find that it's periodic and runs on a limit cycle. So this is exactly this remnant of the scale invariance that remains. It's not a full scale invariance that you have, but whenever you rescale your cutoff by a particularly fixed factor, which is determined by properties of the system like isospin symmetry and particle exchange symmetries and so on. For 3 identical mass bosons, it's 22.7. Then you will get the same coupling constant back. So it's not fully scale invariant, it's only scale invariant under scale transformations with this particular factor. And one can derive an analytic expression for this running and so on. But the physics behind that actually is very simple. And this is shown in this plot here. So here in the inset, you can see this log periodic behavior that this coupling constant has. So it's a periodic function of log lambda. See here, down here, we have lambda on a logarithmic scale. And the way to understand the physics behind it is well, consider what would happen if you didn't have this three-body force in there. Then, of course, the problem would not be renormalized and observables would depend on the cutoff. And what would happen is shown here in this larger plot. So let's see, you have a bound state here at a certain energy, and now you make this cutoff lambda larger. Then this bound state gets deeper and deeper and so on. At some point, there is a new bound state, and this will continue forever. Now, if you introduce this three-body force and set as a renormalization condition that the shallowest state in that system should be at the energy of this green dashed line here, then here in this region, below this crossing point, of course, you need some additional attraction to get the bound state to that energy. So you will need an attractive three-body force here. Once you're beyond that point, without the three-body force, you would be too deep. So you actually need some repulsion. So this is why this turns positive. And then at some point, you reach this line here where there is an additional bound state. So the state that we sat on before cannot be the shallowest state anymore, because there now is another state in between. So the way the renormalization works in this system is that now you jump from this branch to the branch below, and this just becomes a deeper state that can be unphysical, or if you have a system with two bound states, of course, it can also be a physical state. But now here you need, of course, attraction to get up here until you reach this point where you need some repulsion. And this explains this log periodic behavior of this three-body force. Now you can argue this is behavior in a coupling constant, which of course is scheme dependent. What is the significance of that? And the significance lies in this discrete scale invariance, because the discrete scale invariance that you see in the running of the coupling constant, this you will also see in observables. And this is what is known as Efimov physics. So here is a summary of this type of physics. So you look at bound states, at three-body bound states, there is a universal spectrum of bound states that shows exactly this discrete scale invariance. So here in this plot, on this axis, we have the inverse scattering length. So the unitary limit here is along this line. This variable k is an energy variable. So just think of that as the energy. And so for positive energies here, you will have scattering states. Down here, there will be bound states unless you're above the breakup threshold for this dimer state. So here for positive A, we have this universal dimer. Then any three-body state, of course, has to be more deeply bound than this dimer state. And for negative A, there is no dimer. So the three-body states can go all the way up to 0. And these black lines here, this is the scattering length dependence of these states. So this is one prediction of this scenario. And you see the discrete scale invariance along any ray at a fixed angle in this polar plot. So if you have one line by this discrete scaling transformation, you can generate all the others. If you do that for finite scattering length, of course, you see if you go along this line, you connect systems with a different scattering length with each other. So one system with another system. Along this line, which is exactly the unitary limit, of course, you stay always in the unitary limit. And there is a fixed ratio that you get when you take ratios of subsequent binding energies. So if you want to observe this type of physics, there are various ways of doing this. So the most straightforward way from a theorist's perspective would be to look at ultra-cold atoms, where you can vary this scattering length by tuning external magnetic fields. So if you have a sample of atoms in a trap, you can do this. And so you can actually walk along a line like this and observe, for example, loss resonances at the points where these states cross threshold, and you have some resonant enhancement of losses. Now, in nuclear physics, of course, you can't do that. So there, your options are a little bit more limited. But you can look at scaling relations between different states in a given system. So given system has a given scattering length, or if you have more than one type of particle, this plot, of course, would be higher dimensional. You would have more than one scattering length, but a physical system then would be along a cut like the one shown here. And then depending on where you are, it could be that this crosses one line or it crosses more than one line, because you also have to take into account that this universality won't apply to arbitrarily large energies, because at some point you will see details of the underlying interaction. So then the physics just not be universal anymore. So there is a window of universality. So this is shown here by this green circle, and roughly the radius here is 1 over the range of the interaction. And depending on how large the separation between the range of the interaction and the scattering length is, there can be in your physical system, there can be one state and there can be more states. Now, the status to date is that there is no nuclear system where you have more than one state. So these scaling relations so far have not been seen manifested in nuclear physics. That's somewhat disappointing, but there are other features of this type of physics that you can use. In particular, there are universal correlations between different observables, and as I argued before, you can use this type of physics as an expansion point to construct theories for low energy physics. And this has been done for a number of systems, the Triton, helium-3, there are extensions to more than 3 particles. So there is an application to helium-4 and to halonuclei. So there is quite some work in this direction. What I want to talk about in the remainder of this talk is the application to the simplest hypernucleus, namely the Hypertriton. So hypernuclei are nuclei which are not made just from protons and neutrons. Take a
so Hans, is it okay if I interrupt you
yes,
with a question?
Please go ahead.
Just because it relates to the previous thing that you said. So do you know if, given the advances of traps and the technology with traps and being able to isolate a single nucleus in a trap, a single isotope in a trap, do you think there's any chance that in traps there might be a way to control, you know, this to explore the scale aspect of the 3-body system and the Asimov states? Because that's technology that we didn't have in the past.
Yes, so that's a very interesting question. And of course, I'm not an expert in experiments. I think the problem will be that you would need huge magnetic fields in order to change any levels in a nucleus, since the forces are much stronger. So in order to vary the scattering length, the way this is done in atomic physics, of course, this is by shifting the relative distance between different potentials for the 2-body system with different quantum numbers. And I would assume that if you try to do that for nuclei, you would need huge magnetic fields which are not available. But
okay, thanks.
Okay, but maybe there is a way to do this in the future. So the hypernuclei, as I said, are nuclei where you replace nucleons by hyperons. So in a way, you extend the nuclear chart into a 3rd dimension, the 3rd dimension being strangeness. And so you can, if you go 1 unit, then you have hypernuclei with strangeness S-1, and there the simplest hypernucleus is the Hypertriton. So this sits here, kind of the partner of the Triton, where you replace 1 neutron by a lambda particle. So this system now I want to analyze in that framework. So here are just some numbers to put this into perspective. So this Hypertriton, of course, has a quantum numbers JP 1/2 plus and isospin 0, and there very little energy is required to break this Hypertriton into a lambda particle and a deuteron. So just 0.13 MeV. The total binding energy is 2.35, and you see that most of this total binding energy actually is in the binding of the deuteron. So just looking at this number suggests that it might not be such a bad approximation to consider the Hypertriton as a two-body, effective two-body system that's a bound state of a lambda and a deuteron. At least some low energy properties should be able to describe in that picture. And this is also where I'm trying to get to. But for now, let's take this as an example of a three-body system. And of course, it would be also attractive if the Hypertriton, if the particles in the Hypertriton had large scattering length, because then you would have a natural mechanism for this bound state to emerge. So if you look at the leading interactions that contribute to the system, there are now three. And this is of all the S-wave interactions that you can come up with to get to these quantum numbers. So you can have two nucleons interacting in the triplet as one partial wave and another lambda particle. You can have a lambda and a nucleon in a triplet as one partial wave and another nucleon, or a lambda and a nucleon in the singlet as not partial wave and another nucleon. So it's clear that the nucleon-nucleon scattering length in this triplet channel, this is the deuteron channel there, the scattering length can be considered large, but it's not so obvious for these lambda-nucleon interactions. However, in order to make that argument, of course, you have to compare the scattering length also to the appropriate range of the interaction, and the typical range of the interaction for lambda-nucleon scattering. This is provided by 2 pion exchange. 1 pion exchange is forbidden. So you can argue that in these channels, even though the scattering lengths are not as large as for 2 nucleons, they're still large compared to the range of the interaction. So it's reasonable to start with this Efimov picture. So here are some more details. Because you know the lambda system is unbound. From scattering data, there is not that much known, because essentially all the data available for lambda nucleon scattering is at relatively high energies and from the late 60s. And there are some effective range analyses of these data, but they are really inconclusive. So if you look at the scattering length in the singlet channel, could be, according to this analysis, anywhere between 0 and 15, and the effective range between 0 and 15 Fermi, and you have similar ranges for the triplet. Of course, these parameters, there are correlations between these values. And you can find that if you look at the original papers, but this is not very useful to constrain the interaction. In practice, what has been done in order to extract the scattering length, this has always been done by using hyperon-nucleon potentials which were used to calculate the scattering observables, and then these calculations were inverted to learn something about the scattering length. So nowadays, I would say the most sophisticated potentials are chiral EFT potentials. And here by Heidenbauer and company, there is an analysis at NLO with the chiral EFT potential, and they find for the scattering length these values here, A1 is of order 3 Fermi, A3, the scattering length in the lambda and triplet channel between -1.5 and -1.7. So that is not particularly large, but it's a factor 2 larger than the range of the interaction. So we take that as a motivation to start with this scenario. Then, of course, in hypernuclear physics, there is always this question of what is the contribution of lambda sigma conversion effects. So this plays an important role in describing hypernuclei if you do this with standard potentials. From the standpoint of this EFT analysis at low resolution, so if you estimate the typical momentum of the Hypertriton, so here from the total binding energy minus the binding energy of the deuteron, this gives you a good estimate of the typical momentum from the momentum required for breakup, which is of order 14 MeV, whereas the typical momentum for these conversion processes is 300 MeV. So this implies that for the physics of the Hypertriton at low energies, this conversion processes cannot be resolved. So this doesn't mean they're not there, but it's a short-range process, and this is something that will appear in a three-body force. If you're only at low energies, you cannot distinguish this process from a three-body force. It's a different way of saying this. So, and if you then go ahead and try to set up an effective field theory for this system in the framework of this expansion around the unitary limit, if you analyze the equation, you indeed find there is a strong cutoff dependence, so you need to renormalize this because you have a little bit more complicated structure. Now you have three coupled equations, and of course the Hypertriton will be the bound state pole in these amplitudes. And the cutoff dependence indicates you need a three-body force, a lambda NP three-body force for renormalization, which runs on a limit cycle. If the masses of the nucleons and the lambda would be equal, the scaling factor would be the same as for nucleons and for bosons, but since the lambda is a little bit heavier, this is slightly changed. So if you calculate the scaling factor, you get 22.6. You also find, of course, there is no room for excited states. There are also no excited states seen experimentally. So again, this is a case where you only have one state, and you can't learn anything about scaling relations. But this system, as I already hinted, is more universal than a three-body Efimov system if you look at low energy. So you can, for example, calculate lambda d scattering. You see there are two curves here with the inner error band is from what you get from the uncertainty in the chiral EFT input, the scattering length. This outer band is an estimate of this the EFT error of this pionless EFT calculation. Now, but what you find is that these lambda d scattering phase shifts, they are actually very insensitive to the scattering length, or if you take the inverse, this is the binding momenta gamma. So gamma is just the inverse of the scattering length. So they're independent of the lambda n interaction parameters, because as long as you fix the three-body force such that you get the correct binding energy for the Hypertriton. So this is some additional degree of universality that is manifest at even lower resolution, and you can extract the low energy parameters. So you see. In this lambda d system, there is a large scattering length, and this is a factor 10 larger than the corresponding effective range. So this suggests that if you're at an energy range where you cannot resolve the substructure of the deuteron, it might be beneficial to work with lambda-deuteron degrees of freedom. A different way of seeing this is if you look at the structure of the Hypertriton. So if you extract the wave function, you can construct the matter radii and calculate them. And depending on which radius you take, so there is a little picture here that signifies different radii you can define. These are the numbers that you get. Again, there are error estimates that the first row here is the shift you get in this radius if you change the Hypertriton binding energy within the experimental uncertainty, and the lower line here is the sensitivity to the lambda n interaction parameters. If you change the chiral EFT input by 15%, you see that doesn't really change a lot. In addition to that, of course, there also is an error that comes from this pionless EFT itself, which is of order 25%. This is not shown here. Now, if you would look at this system in this lambda d two-body picture, then of course there would be only one matter radius that you can define, which is the distance between the lambda and the deuteron. And so if you do that calculation, you get a matter radius of 10.3. And if you compare that to the corresponding radius in the three-body picture, you get 10.8. So this also is very close, and it indicates that this lambda d picture is not so bad. You look at the extent of the system, the main contribution to its size is from the distance between the lambda and the deuteron, and not the size of the deuteron itself. So in a good approximation, you can treat the deuteron as a point particle for this physics, would be a different way of saying this. So this we take as a motivation to look at the Hypertriton lifetime. And this is a question that has received some additional interest recently. So here is a plot of the Hypertriton lifetime in picoseconds, different measurements over the years. The red line is the free lambda lifetime. And all these black dots here, these are older emulsion experiments that have been carried out in the 60s and 70s, and they all seem to indicate a value that is of the order of the free lambda lifetime, even though there are some outliers here that find some lifetime that is significantly smaller. But then, so since 2010, there has been a renewed interest in the Hypertriton lifetime, because Hypertriton can also be produced in heavy ion collisions. There are experiments at RIC, particular results from STAR, and also results from ALICE at the LHC. And these are the blue dots here. And except for this last paper shown here, they all seem to indicate a lifetime that is significantly smaller than the free lambda lifetime. So this is known as the Hypertriton lifetime puzzle. In particular, there is another feature to this puzzle, which is that this recent STAR measurement, they also measured the lambda separation energy, and they found a value of 410 keV, which is a factor 3 larger than the standard value that kind of was accepted in the community, which is 130 keV. So what we wanted to do is to investigate the lifetime dependence on the lambda separation energy in effective field theory. And because of what I argued before, we wanted to do that in a two-body effective field theory with lambda d degrees of freedom, because it's simpler, and we argue that this will also capture the main physics. So let's look at the decay channels of the Hypertriton. So there are, for the Hypertriton, there are two main decay channels. So one, of course, is the decay of this of the bound lambda particle. With the same decay channels that you would have also for free lambda decay, but then there is an additional decay channel that you have in the medium, this non-mesonic decay, because lambda n can scatter into nn. It's a weak scattering process. However, this process has been calculated by Kamada et al., and it gives a relatively small contribution, 1.5% of the free lambda width. So this is not likely to be relevant for this puzzle we're discussing here. So we'll focus on the decay channels that come from the decay of the free lambda, and their decays into charged pions and into neutral pions. And then, of course, you can decay into the pion and a trinucleon, helium and hydrogen. You can decay into a deuteron and a proton or a neutron, and you can also break up the deuteron. And in principle, there are also leptonic decay channels, but these are at the 10⁻⁴ level already for the free lambda decay. So these this won't matter, and they have been neglected in all calculations. Also, the decay here, where the deuteron is broken up, this is a factor 100 smaller than the other two decay channels. Of course, this is something that we could not describe in a theory with lambda d degrees of freedom. The deuteron cannot decay in such a theory, so we can only look at the first two, but they make up 99% of the total width. So it's a reasonable assumption that it's sufficient to look at these decay channels. So here is a picture of the corresponding thresholds. So you have here the energy. The hypertriton is here. Of course, this is not to scale, right? So it's bound with regard to the d lambda threshold with 130 keV and 2.3 MeV for the full breakup. And these are the decay channels that we'll consider in dp plus pi and also dn plus pi, and in the trinucleon and the pion. So these are the Feynman diagrams that we evaluate for this calculation. So considering the deuteron final state, of course, so you have the hypertriton, then which decays here, splits into a lambda and a deuteron, and the lambda then decays into a nucleon and a pion. So this here, this is the pion. So you might ask, well, how can you have pions in pionless EFT, which essentially is what we're using here, but these pions here are external particles that are always on the mass shell. So this is a process that you can treat in this framework. However, of course, we don't have pions inside loops and in the structure of the hypertriton. Now, this nucleon that comes from the decay of the lambda, this can do final state interaction with the deuteron. This is represented by this diagram. And then we have the trinucleon final state, where the lambda decays, but this hypertriton doesn't break up. It's converted into a triton or helium-3. So these are the processes we can calculate explicitly. And in this EFT that we have, we also calculate them exactly. So there are no approximations regarding phase space or a most probable pion momentum or anything like this, no closure approximation. So we use a simple theory with simple degrees of freedom, but in this theory, we calculate the process exactly. Now, in order to calculate this, in principle, for the decay of the lambda, you can have a contribution from isospin changing by 1/2 and delta I equals 3/2, but the delta I equals 1/2 rule, which is a phenomenological rule that now also, I think, has been explained on the lattice or seen on the lattice, implies that this delta I equals 1/2 amplitude is much larger than the delta I equals 3/2 amplitude. So if we take that into account, the amplitudes for decays into the pi0 and the pi minus can actually be related by simple isospin factors. And this is what we do here. For the final state interaction here between the neutron or proton and the deuteron, we take into account both the S equals 1/2 and S equals 3/2 channels. But S equals 3/2 gives a very small contribution at the order of 10%. The dominant contribution, of course, comes from S equal 1/2. And then the parameters of these interactions here are fixed to bound state properties of the triton and ND scattering properties, and the Coulomb interaction here in between the baryons is neglected. So then we can go on and calculate the decays and the partial width for different decays. And our results are summarized in this plot. So here, so this is a little bit busy. So let me walk you through this. Shown here is the partial width in units of the free lambda width as a function of the lambda separation energy. So this is, of course, one of the strengths of this theory. This is an explicit parameter, so we can vary this very easily and calculate the observables as a function of this parameter. This double line here, this is the free lambda decay width, and the free lambda decay width in units of the lambda decay width is just 1. So this is why this here is a constant line. The dash dotted gray line here, so this one, this is the total width of the hypertriton as a function of the deuteron lambda-deuteron separation energy. So you see this goes down a little bit, but we also, there is an error estimate from the effective theory, and this, you see, it becomes larger the larger this lambda separation energy gets. The reason for this growth is that if the lambda separation energy becomes larger and larger, of course, our separation of scales is not so good anymore, and this lambda D picture breaks down. So we can, if you are the lambda separation energy 1.5 MeV, you see the error is already very large. And this goes down because the further B lambda increases, because now the lambda particle is more and more deeply bound, so it's more difficult for it to decay. If you would look here around the 1, you would actually see a slight increase before it gets down here, because there are additional decay channels. But the region of this small increase is very small here, so you can't see it on this plot. But what you also see, of course, is that this calculation here, it's not very sensitive to B lambda. So the total width of the hypertriton is not very sensitive. And this is something, of course, that also was known before. There is a calculation by Congleton, for example, using that same picture from 1990, which found a very similar result. So let's look at the partial width. So first here, this blue dashed line, this line here, and so for this, no errors are shown, but you would have a similar error band here, which grows with B lambda. You see that this actually gets smaller as you increase B lambda, and this is mainly a phase space effect because the phase space for decay into ND decreases. If you include the final state interaction, you get this line here, and you see the final state interaction actually pushes this down quite a bit. On the other hand, if you look at the width for decay into the trinucleon states, helium-3 and the triton, so this is this dotted line, this actually increases, and that also mainly is a phase space effect here, because the phase space increases relative to the competing decay channel. Now, experimentally measurable is the ratio of the partial width for decay into helium-3 to decay into helium-3 and PD. So there are these charged final states. These are the ones that can be measured. And therefore, we calculated that width also. So this is given by this reddish dashed line here, again with the error band. And you see that this width, this width increases here and seems to saturate around here. So that is the main prediction that can be compared to experiment. These vertical bands here, the green band and this bluish band, give the kind of the standard value of the lambda separation energy with the errors. This is this band here, whereas this bluish band is the star value. And the consensus from emulsion experiments is that this partial branching ratio, which is called R, usually is between 0.3 and 0.4. See, our calculation is consistent with that value. So we are here between 0.3 and 0.4. If we would go to the larger lambda separation energy, we would get a significantly larger value, closer to 0.6. So summarizing these results, and the main numbers on this transparency, the emulsion experiments for this R ratio, they give you 0.3, 0.4. Now, this recent star result is consistent with that value of R, but gives a much larger lambda separation energy of 410 keV. And so this also seems a little bit puzzling, and there are also other calculations looking at this. A recent Norcore shell model calculation by Perez Obiol and company, they found that the star value is consistent with the own value of B lambda if you take into account the corresponding error bars. Our result, these are the numbers extracted from the plot of the previous transparency, are that we get a 0.57 for B lambda 0.4. So this, of course, is different from star's own value. But if you take into account the errors, you also see within 2 sigma it's consistent, within 1 sigma it's not. So you can't really claim that there is an inconsistency, but I would say there is some tension. If we compare our calculation with other calculations that have been done before for this value, the standard value of 0.1 MeV. We get for the total width 0.98 with this error 0.24, this value for R 0.37. And this is in good agreement also with the full Fadeev calculation by Kamada, which was carried out with some of the Nijmegen potentials. So this also indicates, since these potentials have very different input for the lambda n interaction, that once you get the correct Hypertriton binding energy, you're kind of nailed to these results because of universality. Okay, so let me summarize. I have discussed universality in the unitary limit, and in particular modifications that come from discrete scale invariance connected to Efimov physics. We have used this framework to carry out a three-body calculation of the Hypertriton. So I argued that the Hypertriton can be considered an Efimov state. In its description, there is little sensitivity to the exact values of the lambda n scattering length. Lambda sigma conversion physics cannot be resolved and appears in a lambda n three-body force. And the matter radius of the Hypertriton can be well described in an EFT with at lower resolution, which has lambda d degrees of freedom. So this was our motivation to look at the lifetime puzzle in a two-body calculation. We could confirm that there is a large sensitivity of the partial width to be lambda, and we find some tension with the star result for R, which has some tension with the with star's own value for B lambda. And I would argue that important ingredient in resolving this puzzle in the future is to really study this correlation between B lambda and R in more detail, also using other approaches. So with this, I want to thank you for your attention.
Yeah, thank you for the really interesting talk. Are there some questions? I see Philomena has asked some questions during the talk in the chat.
So I'm sorry, I didn't see that.
I'm going to field that right now. So she's asking, have you explored other hyper three-body states like lambda lambda n? And what do we know about the lambda lambda interaction?
So we have also explored the lambda n system. And if you look at, so the lambda n system, if you look at the quantum numbers, so the Efimov effect would in principle also constitute a binding mechanism for the lambda n system. So this is not forbidden by any symmetry principle or so. And the question for the lambda n, so if you go to this, come back to this window of universality. So of course, in the theory, you would find a lambda n bound state, but the question is whether that bound state is within this window of universality. So if you, so this is something that this type of approach cannot answer, because it has to come from somewhere else. If you make arguments about the distribution of this three-body parameter in a particular way that seems reasonable, you'll find that it's less likely than the Hypertriton to be bound, but you cannot exclude it. And lambda-lambda interaction, we have not looked at. So if we, I think other people have done this. So this is, I think Nirbanea and Avram Gal and collaborators, they have also applied pionless EFT where they have looked at different nuclei with a more general set of interactions and fixing the interactions with known experimental facts about hypernuclei, and they could get a good description. They have also looked at the lambda-NN system, and their claim is that the lambda-NN system, existence of a lambda-NN bound state would not be consistent with what is known about hypernuclear interactions. But one also has to keep in mind that their calculation also is a leading order pionless EFT calculation. So there are also errors, and one can discuss whether the result is robust enough to exclude the existence fully, or whether there is still some room.
Thank you.
Hey, Hans, I wanted to ask a question. So I put in the chat. So what is, by the way, I should say that was a great talk. Very, very, very clear and interesting. What is the dominant source of uncertainty in that ratio, 0.98 plus or minus 0.24?
So this error is mainly determined by the typical binding momentum of that system. This is relative to the breakup momentum of the deuteron. And so this gives you this error estimate if you propagate it through.
Okay. So is it clear that it's going to be? Is it clear that it will come up as a symmetrical error? It might be asymmetrical, or?
So the I mean, we estimated it as a symmetrical error. So in order to really see whether there is a difference, I guess one would have to calculate the next order and see whether there is a
okay, thank you.
The change.
Okay, any more questions?
So I have a question regarding the lambda-nuclei interaction. You didn't mention the systematic of hypernuclei as a source of information, I think. Can you comment on that?
Yes. So we this is not used in this study, right? So we I mean, it's used implicitly since we take so the lambda-nucleon interaction we take as input from this chiral EFT. So this, of course, contains some information on that, but we so in principle this is what I also said in response to Philomena's question, that one could extend this theory and look at systems with the larger strangeness, or also at 4 and higher body systems, and use more general interactions and constrain the interaction this way. This is what Avraham Gal and collaborators have done, and then you can make a different analysis about the lambda-NN. For the Hypertriton, for the analysis I was considering here in this lifetime analysis, this wouldn't make any difference, because there would be one three-body force in that particular channel, and this you have to take from the lambda separation energy of the Hypertriton. So this would not this would not give you any additional insights. For the lambda NN system, you could gain something by doing that.
Okay. Thanks.
Okay. Any more questions? If that is not the case, then I would like to thank you again for the very nice